my name is Hee-Soo Lee. As you know, the introduction.
Uzi.
Yeah, I work for Keysight as the product owner for service-related applications. I'm very, very happy to be here to talk about today's presentation, which is something around the PAM4 for a 400 gigabit applications. It will be quite a broad in terms of topics I'll be covering. Talking about the PAM4A signaling, and then I'll be talking about the application space where we can see basically what about the interconnects as well, how we go about the modeling of those interconnects, and also thinking about the modeling of the transmitters and receivers. And then finally, we're going to put everything together to make up a reference designs for 400 gig data center application boards. Then we probably go for the Q&A. So let me start with this PAM4 signaling. As you can see, NRZ is basically non-return to zero, or we could call it PAM2 because there are two levels, right? And when you look at the PAM4, well, that has basically four levels. So looking into the waveform, it's a little bit difficult to say four levels, but when we are starting to look into it within the eye diagram, we can clearly see that there are four levels instead of two levels, 0 and 1. But for PAM4, there are multiple levels. So with the NRZ or PAM2, basically it is a transferring information of the basically 1 bits, which is coming with the 0 and 1. But with the PAM4, it is sending the 2 bits along with that symbol. So you can see that probably 0, 0 and 0, 1 and 1, 0 and 1, 1. So why people are doing it is because it increased the throughput of the system with the based on this different type of signaling. So if you look at PAM2, in case of PAM2 or NRZ, 106 gigabytes for a 56 gigabit per second. So same bit rate for the same baud rates. However, when you look at the PAM4, it is actually going to be 28 gigabytes for 56 gigabit per second a transmission for the system. So basically that means you have the 2x throughput for the same baud rates. That is one of the reasons why many people are using the PAM4. The other benefit, when you look at the basically Nyquist frequency or a spectrum data, as you could see, this is a NRZ or PAM2, green color, but this is a PAM4. That basically means Nyquist a frequency for PAM4 is half of the PAM2. So think about it. You have the same channel. Let's say it's a 10-inch transmission line, right? But since you are sending the smaller bandwidth of the data through the same channel, basically you can get a less loss coming from the same transmission line system. As you probably know, for FR4, there is the 0.1 dB kind of loss per inch per frequency as a rule of thumb. So if you are using the same formula but reducing the frequency range, that you can start to think about, yeah, I can get the smaller loss. That means you can actually make the design much more efficient. So that is one of the reasons why people are using the PAM4. Basically sending the higher a bit of data with the same channel structures or size of the transmission lines. So as you can see, it's not always good. If you look at the voltage level for the NRZ, here is the clear 0 and 1, and the level between the two are clearly wide. However, since we are using the full levels, as you can see, voltage margin is going to be smaller compared to the PAM2. If we are putting the number into SNR, signal to noise ratio calculation, you can see there is a little bit of a 9.5 dB smaller value for SNR by using the PAM4 signaling than PAM2. right? So as a summary, why people are moving to the other PAM4 is because of basically the speeds. Higher a throughput for the system by using the same transmission line structures. But along with it is a benefit, but also we also need to think about the smaller noise margin. So not always good things happening with the PAM4 because there might be a little bit more challenge. But there is no question, especially for the data center, just booming, and they are pushing a lot more data, where they really need to use the existing structures to pump up the data rate. That's what more of the PAM4 is preferred. So going into what applications are using the PAM4, we can start to see a lot of different standards. For example, 400 gig class standard and IEA, which is implementation agreements. We can see that IEEE 802.3bs, which is defining the 200 gig and 400 gig AOE for chip-to module or chip-to-chip. All of this, 802.3CD and OIF CI 56 gig, short reach, very short reach, and MR and RR are also using the PAM4 signaling, all right? If we are looking into the more of the optical standards, as you can see, 802.3bs and CD defines are for a 200 and 400 gig. They are also using the basically PAM4. So the point is PAM4 is everywhere, especially looking into the Ethernet application. PAM4 is the dominant signaling type for Ethernet applications. I had a little bit of issue when I started to look into this Ethernet applications, which was more on the protocol name. So how people are defining the name of the protocol. So that was quite interesting thing. And I searched through it. I found quite a good information from internet based on the Intel's kind of white paper. So how people are defining the name of the Ethernet, it starts with the total data rate. When people are starting to say 400 gig base CR 8, then how we interpret it is basically the first number is the data rate, total data rate. And second is just base. And third one is talking about the medium, all right? So if it says CR, that means the medium for that interconnect is used, the copper cable is basically used for that transmission medium. If somebody is putting the KR, then that means basically the backplane for the media. And SR, MR, LR, or ER are all about the optical communications. And the last number would be more like how many lanes are used for that specific standards. Then we can start to look into somebody calls XAOE or somebody calls CAOE or CD AOE. These are all interesting numbers, but everything is based on the Roman numerals. So as we all know, X stands for 10, C stands for 100, D stands for 500. So XAOE means basically 10 gigabit system. But somebody says CD AOE, that means C and D. We put the D first, 500, and C minus, that means 500 minus 100, which is basically defining the 400 gigabit system. So this is the kind of way we can understand those standards defined for the Ethernet applications. So again, CD AOE means 500 minus 100. That's basically 400 gigabit system. So let's talk about the Ethernet application space. This is the more of the typical implementation. One example I'm using here is the Ethernet switch using the 400 gig base FR48 optical link. So if you look at, here's a switch card, a backplane, and line card. These are all the connections. Every single area, you see the different type of standards. For example, between the switch ASIC and retimer, you are basically using the CI 56 gig VSR, or in terms of signaling, that is basically using the PAM4 or NRZ. When you go into the back plane, basically this is the standard, and between the retimer and host ASIC, that's the kind of standards. So this is basically a typical application space for Ethernet, and we'll be looking into the other, all the details, one by one. Looking into more of the interconnect application space, there are a lot of different ways. For example, you can actually make the interconnects between die and die to die. But these die to die are within the one MCM multi-chip module. Then the interconnect between the two might be a little bit different compared to the other PCB structures. But also you can make the other die to nearby OE. OE means optical engine, right? So basically making the connection between electrical to optical, chip to nearby OE. There are a lot of different ways, including the chip to module interconnects. So these are a very typical interconnect application space you can find for a typical Ethernet applications. So let's take a look, one simple one. Here's you basically have a chip, and then from the chip you have a VS, solder balls, and then going down to the board level through the VS structure, and there is a transmission lines and another via and connector, going through the back plane, and then coming back to this, right? This is a typical entire interconnect for the design. Then basically we will be starting from this chip level, which is basically a transmitter, or it could be a receiver. So if we are sending the data from this top chip, this is basically a transmitter, and the receiver will be at the bottom, which is basically a source of the the transmitter and receiver, which is transmitting the data from the TX to RX. Then when we are looking into this transmitter and receiver, we got to have a way to represent the chips, right? How are we going to do that? Some people might use the circuit level, like H-Spice or Spice motors, to represent those chips. But will be very, very inefficient because you have to simulate the entire transmitter and receivers at a circuit level, which could be hundreds or thousands of the different components. And also, if you're thinking about the serial link or SerDes, you really need to process the millions of bits. It's going to be very, very difficult to simulate it with the Spice-like simulation technologies. So one way industry developed to represent its transmitter and receivers is basically something called IBIS AMI. So it is using the IBIS definition to represent the chips and buffer information, but algorithmic part, especially for SerDes, that includes the CTLE or DFE type of equalizations, and along with the CDR, clock data recovery. Basically, it uses the algorithmic interface to represent those DSP functionalities. So all the other standard SerDes channels are something like this that has the transmitter, which has the certain equalization such as FFV, and then there is input bits coming in such as PRBS, and there is the bits coming into the package. And then going to the channel and receiver end, there will be a RX package, and then it goes through those receiver equalizations that includes a CTLE, DFE, and CDR. So how things are represented? Definitely this TX package data, RX package data will be a part of the standard IBIS model, but this algorithmic part that is basically used at something AMI extension, which is called .AMI file, all right? So when you are combining this and then pass all the data through a channel, then you will be able to run the entire structure with a channel sim, which is really, really fast simulation technologies. But one of the reasons why people are using this IBIS AMI is because that is basically coming with the more like a DLL or .so file, which means they don't need to reveal their IP. It's such not like the SPICE circuits, right? Therefore, showing all the necessary capabilities and characteristics of the chip without revealing their own IP information. That was one of the main reasons why people developed this IBIS AMI, which is extensively used in a services market. So one question is, okay, IBIS sounds good, IBIS AMI sounds good. How accurate they are? So I wanted to put a couple of examples that shows the accuracy of IBIS AMI model. So here is one example, which is showing the one side measured data, and the other is simulated data with the AMI model. But simulation is really fast, and looking into the accuracy between the two, it looks very good. All right, and then the other way to test it is creating the other kind of data, and then download a simulation model of TX to AWG, which is arbitrary waveform generator, and then we basically simulated the channel data, which is a dot here, and put into a schematic in a like ADS, and put the IBIS AMI model for a receiver. So this represents the entire channel, including the TX and RX, and at this bottom, it is really generating the waveform data with AWG, and then measure the dot data, which is real a PCB data, and then get the output data at the other side of the channel and compare to the simulation. So as you can see, PAM4 data coming out from the receiver compared to the other measured data, they are very similar to each other, which is really showing the accuracy of the IBIS AMI model, right? So how really things work for TX and RX, algorithmic part is represented by .dll or .so file, which is pretty much compiles data from the chip vendors. TX analog and RX analog, which is the package information along with the channel data, these are a more like software vendor like Keysight, ESOP are simulating. But this green color data is something like chip vendors will provide a design engineers so that they can represent the chip information for TX and RX properly, and then the EDA vendor will assimilate all other things such as the channel along with those package data, right? So let's take a quick look on interconnect modeling. Going back to the same graphic that I was showing you several pages, the slide ago, before. This is the typical interconnect space. As you can see, you see via and trace and connectors and vias and trace and vias coming back to the other trace to this receiver. As you can see, there are a lot of transitions, a lot of interconnects. Probably I say, based on all my last 30 years of experience, I can say trace is pretty stable in terms of sending the data or carrying the transmission line of the signals. But all the problems are coming from the from the via structures or interconnects. It's because it's very difficult sometimes to define the return path. And there will be a unnecessary coupling happening between the differential vias and to the ground planes and so on and so on. So you really needed to be able to model all the interconnect properly so that along with those chip data represented by IBIS AMI, you will be able to simulate it properly and then compare to the measured data with the highest possible accuracy for the design. So how are you going to model them? There will be multiple ways. I don't think there is only one single way. Some people prefer to go with the full wave 3D EM simulations, such as FEM or FTTD, whatever. But some people might go with the rule of thumb. But I always tell people there are three pillars. One is the speed of the simulation or modeling, and the other is accuracy, and the third thing is the capacity. So if you are really looking for the ultimate accuracy, then it's always better to go with the full wave 3D modeling, but at a cost of the modeling time. It may not be that simple, or it may not be that speedy, but again, if you're really looking for the ultimate accuracy, the full wave 3D EM models is the best. However, sometimes you can go with the quasi-static models, which is saving at the same time. But also, by choosing the quasi-static models, you can actually simulate a lot more than the full wave 3D EM models, right? So there are multiple considerations, but again, there isn't just one single answer to it, because based on your need, you need to think about speed, accuracy, and capacity for your design so that you can properly model your interconnects without having that much of trouble. Then when you start to model your interconnect, you have to think about what's the bandwidth, right? I can tell you, a lot of the analog design engineers, to them, the bandwidth means F low to F high, which is a specific bandwidth. For digital design engineers, bandwidth basically stands for DC to F max, right? So this is one of the difference between the analog engineers and digital engineers. The way they define the bandwidth is a little bit different. So why we are thinking about the bandwidth? Because when you model your channel, you have to think about how high I need to model them, right? So one way of calculating the bandwidth, especially for the digital designs, you can go with the one bandwidth calculation, which is very typical based on the 3 dB bandwidth characteristic, using the simple formula of 0.35 divided by rise time of the signals. Or if you are looking for the more of a spectral energy density related calculations, you can use the F-knee frequency equal to 0.5 divided by the rise time of the signal. But interesting thing is everything is related to the rise time of the signal, right? So what if you have the rise time of your waveforms? Then you can easily calculate the necessary bandwidth for the channels. But what if you don't have them, such as some kind of DDR applications? Then you could possibly use the slew rate. For example, here, 4 volts per a nanosecond, or 9 volts, per a nanosecond. This is the typical slew rate. You can use that to calculate it. Basically, if you tend to use this slew rate to calculate the rise time, you can actually get the pretty simple calculation, and we'll be able to get the rise time of the signal, such as the 51.4 picosecond. Based on this, you can calculate putting this number back to the bandwidth calculation. You can actually calculate the bandwidth of the channel data or knee frequency. But if you don't happen to have this type of slew rate with your waveform signals, then probably you can use the other kind of rule of thumb. Just data rate times probably 2. That gives you pretty sufficient bandwidth or channel data. That's one of the simple way to calculate the required bandwidth. So now we got to we have the channel data. Then how we can assure the accurate channel modeling? There are multiple ways, as I talked about, but one of the quite nice way, I call it more like a mixed domain approach, is another good way of modeling your channel, shooting for the accuracy and speed at the same time. What exactly is that? It's basically focused on all the the via related a simulation with FEM, all right? And then trace-wise, we can simply use the quasi-static solver. Then combine them, and we get the really accurate simulation results. Once again, when we have a certain interconnect that comes with a via transmission line and via, all the transition issues or problems coming out from the channel is coming from the via, not the transmission line. So sometimes you don't even need to simulate the transmission lines. It's because most of the designs, they just follow the design rule. For example, in order to maintain the 82 ohms for differential, they certainly know what's the width of the copper and what will be the space between the ground planes to the copper. And they just follow, and then they put the really ground planes in a very solid ground plane. That's where there is no much of problems or issues. But as soon as it goes to via structures, that's where all the problems coming out. That's where we can actually put a lot of more, the tougher simulation to assure the accuracy of via transition. This is what I call the more of the mixed domain. Simple simulation for transmission lines, but tougher and accurate simulations for via structures with FEM. So here's an example. This is the one kind of case. If you look at this is a TDR application, DQ lines. The line length is pretty long, starting from here to there. The line length in between is about 3 inches, and then input and output there is a via structures. So instead of putting this everything into a full wave EM solver, again, it takes quite a long to simulate it. So why don't we just chop it, only transition area for A input, same for the output, and then in between just represent it, with a simple cross-sectional solver, and representing the right length of the transmission line. Then you get the very accurate simulation results between the measured data compared to this simulated structure, which I call the mixed domain. But if you have a time, you have a bandwidth, then you can go with a full wave EM, but you don't really have to do that because you will be spending a lot of time to analyzing those transmission lines, which is not really necessary to be simulated with the full wave EM solvers, right? Okay, I'm sorry. So here is another one, showing that simple example. If you look at this is differential pair, not single-ended. So that black box area is basically represented as a very simple transmission line, single straight line, even not serpentine, type of transmission line. And then this part is basically this interconnect parts are simulated with a full wave, and then let's combine and then simulate it. Then comparing to the measured data, which you see here, this is a very, very decent agreement between the two. But you don't have to simulate the entire traces, which is having the really long transmission line with a lot of bends. Although we represent it, with a simple straight line, the accuracy between the two are very, very close. But important thing is this suck out, which is coming from the back drill, the via stub, that is really captured very well because that's the section we use the FEM solver to analyze those via transitions. So as long as you put a really much of effort to accurately model the via structure, then the other part of the design can be quite simplified, like what you were seeing. And when you are going into those channel modeling, especially with using a full wave EM simulation technology, you probably need to start to think about how you represent the ports. Why is that? Is because there are multiple type of ports. Somebody called LUM ports. That is very simple, nodal based source, which basically means you put the 2 pins and then connect the current source to drive the structure. That's basically LUM port. And there is another, something called a She port, which is creating the kind of structure and multiply all the, the currents. so that you can reduce those parasitic inductance coming with the ports. Other type of source is something called waveguide ports. There are multiple different type of ports. Why there are multiple is because that's basically what most of the EM solvers have their own internal sources. But in order to provide the best accuracy, waveguide port is the best. There is no question about it. But certain structures, for example, like when you simulate the VS structure, it may not be that easy to create waveguide structures. That's where you probably need to go with a lump port or a sheet port. So that's why most of the EDA vendors are providing those different type of source. But again, since waveguide port is the most accurate port, it's better to go and use those waveguide port as much as possible. But what if you happen to have a kind of structures you got to use the lump or a sheet port? Then you can actually think about how the calibration of the structure with that type of ports. Here is a simple one I can show you. If you look at this, the red data is basically waveguide port. And then same structure, but when you are using the lump port, this is a green data. There is no difference between the structure, just different type of port. You can see that the return loss changed quite a bit. Why is that? It's because lump port comes with its own parasitic inductance. So how are we going to de-embed that out? Here is a simple test structure I created. I put the inductor to the structure EM simulated with a lump port, but the inductance value for that inductor is negative inductance, right? When you put this negative inductance and try to tweak or tune, then you can see that this one moves quite a bit. By doing so, you can extract what is the port parasitics along with the other type of a lump port. So in this case, I came out with the 145 picohenry, which is the more of the parasitic inductance associated with a EMA simulation. Once you know them, then you can use this value whatever you simulate. Is because that will be representing the port parasitics with certain PCB structures, so that will help to increase the accuracy of the simulation. And another kind of interesting thing when you are thinking about this high-speed digital board designs and simulations is basically voids on the ground plane. Some people happen to create the kind of voids on the design, on the transmission line structures. Sometimes it's really unavoidable due to the signal power ground bias. So when you happen to have this type of problem, what problems specifically we need to deal with is more of the mode conversion. That is what it really matters. If you look at this structure and what I did, basically making the size of this via anti-pads larger and larger so that it actually eats up the ground return under those transmission line structures, then you can see how much of the impedance is fluctuating, or the STD transmission is fluctuating. But looking into it, it's not so bad, although it changed quite a bit, but it still remains within the few dB scale, which was quite a surprising data. But important thing was this STD or STD11 or 21 is smaller variation compared to CD or DC, which is really directly related to the mode conversion, all right? So the more problem with those type of perturbation on the ground return is actually creating the more of mode conversion, which is the problem related to the more of EMI EMC issues. Same for when we are looking into, again, when we are looking into this DC component, Now you see that that smaller a perturbation is just creating a lot more a fluctuation on the data. So that's what I meant by it's important to looking into those mode conversion data instead of just looking into the other differential components. So this is voids. The other is a slot, right? Slots sometimes, they happen to be in the design due to the layout, kind of, concerns or issues. Again, if you look at this is a SDD and this is SCC, we see more impact on common modes. It's because the differential mode is basically running signals on those top A2 copper. But when you think about the common modes or common signal is really flowing through the ground plane. So we made it a kind of slot on the ground plane. That's why it is affecting a SCC data a lot more than SDD. We don't even see much of variations for SDD, but I can tell you SCC is changing quite a bit. So looking into these DC or CD components, now you see that there will be a lot of fluctuation by the how much of the slot you are creating, and also by looking into all the field data, you can see there is more problems with this common mode than a differential. So which one is really worse between the slot and the voids? Based on all the tests what I have done, void is not big deal, but slot is a lot more problems. It's because it just creates more of the mode conversion, or generating more of common modes, which is affecting the system EMI, EMC issues a lot more. So a little bit more caution needed to be put into slots than voids, right? So finally, moving into the put everything together. So again, if I just step back and tell you about it, we went through the signaling. So PAM4 is the main signal for Ethernet applications. And then we have to think about how we're going to represent the transmitter and receiver, which is the IBIS AMI part. And then how we're going to go about modeling of the channel, which is the one we just talked about. Once you have all of them, you just need to put everything together and run through the simulator like a channel sim. You will be able to get really accurate simulation data because you have a good IBIS AMI model for your transmitter and receiver, and you have a good channel data, then nothing to worry about, because that's the way to guarantee your simulation for the design to be matched with the measured data as close as possible. So there are a lot of the different annexes. For example, for 802.3 BS and 200 gig and 400 gig over optical link, there is the C2M or C2C AUE annexes. Same for the CD applications. But when we are looking into it, basically, we can find that Nyquist frequencies is about 13.28 gigahertz. So that means, although we push into the 20-something gigabit per second, still Nyquist frequency will be a lower side, which is one of the reasons why people are using the PAM4 to speed up, or boost up the throughput of the design. So for the compliance, there are two ways. One is using COM, channel operating margin, and the other is using the iMask, all right? So in this test case, we will be using the iMask. So how you set up those measurements is basically, this is the standard Annex 120E, define the test setup from TP0 to TP1A plus scope. So using the PRBS13Q as the test pattern input, and here is the host board, and there is a host compliance board, and basically you need to measure it with a scope at a TP1A. But specification really says when you do that, you really need to put the fourth order Bessel-Thomson low-pass filter along with the CTLE, which is continuous time-based linear equalization. So you have to follow this specification because this is what a Onyx 120E specifies or defines measuring a certain part of the design. So I'm going to skip this. Here's the actual design. This is the design actually. I don't know how many of you know about IXIA, but IXIA is a part of the Keysight. They are doing a lot of data center type of applications. So we worked with them. So this design is a real design. But if you look at this is a TX AMI, and here's a TX package, and this is the board trace, another board, and going back to the RX. But within this structure, there is a lot of the complicated designs, a lot of the transmission lines, and some of the connectors. Everything is just embedded into it. Then you can put something called iProbe to measure any of signals and being able to plot those data. But again, this TX AMI is from one of the chip vendor, and RX AMI is coming from another chip vendor, so that you can see finally the output data, which is right after the RX AMI. Then you can see the I is quite well opened. But right after the channel, you can see that I is quite closed. But after the applying equalization, including the CTLE and the DFE, you can make the I quite open. But one of the issue with this is based on the previous slide that defined the Onyx 100 defined by Onyx 120E. You have to put the fourth order Bessel low-pass filter along with the CTLE only, not DFE. So in the case, how are you going to set that up? So here, if you go into the next slide, same design, but instead of using the custom or vendor IBIS AMI model that represent the RX, basically you can use the more of the generic one. That with generic one, you probably will be able to do only CTLE because you can turn on and off a DFE. With this, now you can see that all different results with a different value of the CTLE applied, right? So if with the 3 dB CTLE, now I can see I data quite open and very clean. But if you are increasing the CTLE to 9 dB, you can start to see there is quite a distortion of the I data because it's over equalized. So by doing it, you can basically being able to see all the proper results applying the different value of the CTLE. But still, one of the problem was missing the fourth order Bessel low-pass filter, according to the specification. So here, finally, we made up the another capability which is called a FlexDCA probe in ADS. This is fairly new. Started to be shipped around October last year. Basically, what it does, it works same as the iProbe, but instead of using the ADS to display all the data, you can basically send the data directly to the instrument, which is a DCA, which is a sampling oscilloscope. So when you do that, what you're gonna get is all the data populated in basically a DCA scope, where you can put another math functions. If you look at the top side, you basically see the fourth order Bessel low-pass filter. You can put that, and then you can put the CTLE applied with more of the preset. Then you'll be able to capture the F1 data, which is the results of a combined with a fourth order low-pass filter along with the CTLE to the simulated waveform. This is the way you can actually meet up your simulation results comparing to the specifications such as Onyx 120E, right? So again, you can actually stay in the simulation environment like ADS and being able to do all of this, but actually you can use the scope as another platform to be able to do all the measurement following up the given specifications such as Onyx 120E, right? I'm going to skip a short demo and any questions? That's really a great question. I will just give you a very simple way to explain it. So if you look at, this is the one section, and where I need to chop, right? So one way of doing it is looking into the via, and you got to have a certain length to stabilize all other modes, right? Then you got to have the certain length. That's the important part. And second is, this section is going through a lot of VGA vias, where there will be a coupling, right? So I'm maintaining the length of the line to the exit points of the VGA. So that's the one way of specifying the good size of the via transition. And then same for this one too. That was exactly done in the same way. So that's the one way. Probably consideration. The other was, if you look at this, it's the same, right? And another design may come with using a layer 3 or layer 5 or whatever, and then certainly switch it to the different top layer due to the different the line width of the transmission line. Within the BGA, you may have a smaller, and when you fan out, you may have a larger. You really need to include them into the fan part. Once you exit that transition part, everything else you can actually put as a simple quasi-static 2D models. Does that make sense? Okay. Any other questions? Yeah.
By the end of the presentation, you showed a channel which at first sight doesn't appear to meet the standard. Mm-hmm. And then by replacing the actual silicon transceiver model in IBIS with the generic receiver model, mm-hmm. You can show that it does meet the standard. But what if the actual channel is designed to actually match whatever silicon receiver I have? Mm-hmm. Let's say the receiver has some imbalance to it or the wrong impedance, and so the channel matches that. The simulation would show that the channel is operating correctly, but it's not compliant to the standard. Because if you use the actual some RX stiff model, which is the standard model and not the measured one, it would fail mm-hmm. To show the eye opening and the rest of it.
That's another great example or great question, where I always feel there is a little bit of uncertainty. For example, when you put the generic, how do I represent the chips package information properly? And when I use the IBIS AMI, which comes with the old package models and so on, but I cannot really get rid of the DFE. How can I do that? This is where probably engineering judgment needed to be made properly. And in this case, the way we did it is basically sending the data right after this channel, right? And then process everything in measurement software, where I can apply data, proper equalization and low-pass filter that represent the scope, characteristic. But still, there might be some uncertainty. That's something, I believe is quite difficult to avoid. That's something, we have to live with it.
Can you please elaborate about the type of corners that you use for this simulation?
Yeah, in this case, I chose the typical, but, in IBIS AMI model, I can tell you this is actually Broadcom chips, right? You can go in, you can select the different corners, and then run the analysis, But my simulation, this specific simulation, was based on the typical corner case.